So, this week's topic holds a special place in my heart due to a whole class blunder that happened in graduate school. So, during my second year of teaching, I was taking this night class for teaching secondary mathematics, and it happened to be on geometry, and we started learning about this topic called taxicab geometry. So, my professor says, draw a circle, and then she leaves to go make some tea. And so, we're all looking at each other like, okay, cool, like, we'll draw a circle. So we draw a circle because we all had our compasses, drew the circle, and she comes back and wonders, well, why didn't you guys follow the instruction? We didn't realize that when she said draw a circle, she meant in taxicab geometry. So she didn't necessarily state that, she assumed it, and so we all had to think about, oh, well, what's a circle in taxicab geometry? So that brings us to this week's topic. So you're probably wondering, well, how is this circle different in taxicab geometry? So before we answer that question, let's think back to a couple weeks ago. I did a video on geometric shapes, and towards the end of the video, I introduced a Greek mathematician named Euclid, and he is known as the father of geometry. So the geometry taught in schools today is known as Euclidean geometry, and some of you may not have actually realized there's many types of geometry, and that's right, there are quite a few. But we're just going to talk about one new one today, so you'll have to look up some of the others. So now let's circle back, get it, to the original question posed by my professor, which was draw a circle in taxicab geometry. So answering the question involves taking what you know about a circle and applying it to how a taxicab would create that circle. So if we imagine living in a city laid out with grid lines like a coordinate plane, if you needed to get somewhere, you couldn't just take the direct path, you would have to cross the grid lines. And we can't do that in a taxi cab. That would be just like, cutting through a block. So you'd have to make left and right turns and travel the blocks on the city streets in order to get where you were going. So to better illustrate this point, let's look at this diagram. Using traditional Euclidean geometry, we could draw a line connecting the 2 points, as it's illustrated by the green line. And if we wanted to find the distance, we would use the Pythagorean theorem to find the distance, which in this case is approximately 8.49 units. However, in taxicab geometry, we can only travel along the grid lines illustrated by the red, blue, and yellow lines. This is because taxicabs only drive along streets, they don't travel through buildings. So then the distance now between those 2 points is 12 units. While longer routes can be taken, distance between 2 points in taxicab geometry is always the shortest route along the grid lines, no matter how that route looks. So since we're talking about distance, let's compare our traditional Euclidean formula to distance to the taxicab formula for distance. The Euclidean formula is derived using the Pythagorean theorem and 2 general points, x sub 1, y sub 1, and x sub 2, y sub 2. In taxicab geometry, we can't create a right triangle in which to apply the Pythagorean theorem. So instead, we have to use this idea of distance along a grid. So since distance is never negative, we're going to use absolute value, or modulus. So for example, the taxicab distance between the point 6,2 and 3,7 would be calculated by taking the absolute value of 3 minus 6 and adding it to the absolute value of 7 minus 2, resulting in 8 units. So once again, let's go back to what a circle is in taxicab geometry. So traditionally, we define a circle to be the set of points which are equidistant from a center point. So for example, if we find all the points that are a distance of 4 units from a center point, we would have a circle with radius 4. So if a taxicab were to drive to all points that are 4 units away following the grid lines, it would look like a square, not a circle. And to shake things up even more, let's think about the value of pi in taxicab geometry. So in Euclidean geometry, we take pi to be the ratio of the circumference and the diameter of a circle. So this holds true for all circles. So what we just learned in taxicab geometry, a circle is actually a square. So we use the example we had earlier. We have a circumference, or perimeter, of 32 units, and a diameter, or the length of the diagonal, of 8 units. This means that pi is equal to 4, because we would have 32 divided by 8. And as it turns out, this actually holds true for all circles in taxicab geometry. How crazy is that? So that's going to be it for this week, but I encourage you to think about what happens to other shapes and geometrical properties in taxicab geometry, because we just learned that a circle is actually a square. So if you want to complete some additional problems on taxicab geometry, there is a worksheet that is located at the link at the bottom of the screen. So just go to it and it's got all types of problems that you can work on that are all in taxicab geometry. And until next week, I hope you guys have a wonderful Memorial Day weekend and, keep being safe out there. Bye.